Okay, everybody, let's get started. Thanks for coming. Those in person, also on Zoom. It's a real pleasure to welcome Professor Vidya Madhavan from UIUC to Caltech today. So Vidya received her PhD from Boston University and then went on to do a postdoc at UC Berkeley. During this early phase of her career, Vidya focused on several things, but perhaps she's most well known for her studies on the Kondo effect, which is the screening of an impurity spin due to a cloud of conduction electrons in a metal, and using scanning tip-based tunneling measurements on cobalt atoms on gold substrates. Vidya performed some real breakthrough measurements in understanding this conduction cloud and its excitations. In fact, she was the first to show direct spectroscopic signatures of what are known as Kondo resonances using scanning tunneling microscopy. After that, Vidya moved to Boston College, where she was an assistant professor. And during her time at Boston College, Vidya continued to advance scanning tunneling microscopy for studies of various exotic quantum materials. She worked on the cuprates using STM to understand the interplay between superconductivity and competing orders such as magnetism locally. Vidya made a lot of contributions to the study of surfaces of topological materials in its early days. And since 2014, Vidya has been a professor at UIUC, where she's not only continued advancing the STM technique to look at topological and correlated materials, but she's also built up quite an effort in growing quantum materials and merging those efforts with her scanning tunneling microscopes. And in recent years, Vidya has done some beautiful work imaging what are known as these exotic Majorana fermions and some exotic topological materials that we'll hear about today. And for all these, Vidya has been recognized in numerous ways for her contributions to condensed matter physics, perhaps most recently by being named a fellow of the Moore Foundation as part of its ethics program. So with that, welcome Vidya, and take it away.
Thank you very much, David. I think that was the nicest introduction I've ever heard. Thank you so much. And one of the most accurate ones. Okay, so feel free to interrupt me. David's told me this is a mixed audience and that you're probably from many different fields. And I hope today to convey the excitement in our field on the possible sighting of these exotic particles called Majorana fermions. As with any new advance, it's not set in stone. We don't know whether what we claim are Majorana fermions are indeed Majorana fermions. But what I will show today is actually how you might even ask questions, right? What do you ask? How do you realize a Majorana fermion in a condensed matter system? What are the signatures of Majorana fermions? How may we distinguish these particles from other particles that you may see in these materials, and so on. Okay, so without further ado, let me just start. I think I'm going to wander. Sorry about that. I try to get as close as possible. Okay, so let me know if this is a problem. Is this because the Zoom people can't see me?
It's because we're very
Okay, if you can't hear me, please let me know. Okay. So let's just start with a very simple thing, which is the Dirac equation. Many of you are familiar with this. This is the relativistic version of no.
I'm sorry.
Okay. I'm stuck here. Okay, so you're all familiar with the Dirac equation. This is the relativistic version of the Schrodinger equation, and actually Paul Dirac wrote it down in 1928. And immediately he realized that there are consequences, right? So one of the biggest consequences of the Dirac equation is the fact that you have these negative energy solutions. And it wasn't very clear at first what these negative energy solutions are. Now we know that they're antiparticles. However, at that time, there was a lot of argument about what these might possibly be. So finally, over decades of work, it's been established that these negative energy solutions are indeed antiparticles. One thing I want to point out here is that, sorry about that. So if you have massless Dirac fermions, in my talk today, I'll often be showing you plots like these, which is the energy momentum relationship. So when you have massless Dirac fermions, the relationship between energy and momentum is linear. And once you add some mass to these Dirac fermions, for example, if you have electrons or any particle that's traveling at high velocities, then any massive particle, then the relationship between energy and momentum looks like this. And in this particular case, for example, all of these positive energy solutions might be electrons, whereas the negative energy solutions are positrons. And because electrons have mass, a charge, the positive energy solutions have negative charge, as we know, electrons have negative charge, whereas the antiparticles have positive charge. Now, about a decade or so after Dirac wrote down his famous Dirac equation, Majorana came up with another equation to describe fermions that might be their own antiparticles. So, for example, the positron is the antiparticle of the electron, but the electron and positron, like I said, have opposite charge. However, if you can cook up a scenario where you have chargeless fermions, then you can actually, as it turns out in our universe, have fermions that are their own antiparticles. So if you have a particle that it's its own antiparticle, you can imagine that these can both annihilate each other. Even though our universe permits the existence of particles that are their own antiparticles, so far, no Majorana fermion has been observed in nature. One of the most promising particles is actually the neutrino. And we've been trying for many years to figure out whether the neutrino is a Majorana fermion. There are a lot of very sophisticated experiments that are being set up to determine exactly this. So one of the experiments to determine whether the neutrino is a Majorana fermion is this thing called neutrino-less double beta decay experiment. So usually when you have these double beta decay experiments, you have the atomic nucleus disintegrating into 2 protons and 2 electrons, and plus antineutrinos. However, if neutrinos were indeed Majorana fermions, there might be situations where these neutrinos annihilate each other, in which case you might get neutrino-less double beta decay experiments. So such experiments are being planned. This is one such example. And you can see here, this is called a Majorana demonstrator. It's 40 kilograms of germanium buried deep inside the earth and so on. And the whole purpose of this demonstrator is to determine whether a larger such experiment would finally prove that neutrinos are Majorana fermions. Yes?
Sorry, would you mind stopping share? We're struggling to get, there seems to be some slide advancing.
Oh, okay, of course, of course. So what's going on?
Slides were advancing.
Did you ask them if that's good? So should I, let me go back. Do they see that?
Yeah, that's fine. Just
Yes, we can see that on Zoom.
Okay, good. All right. Sorry. Let me actually close myself here. Hide video panel. Okay, good. Okay. So over the last 15 years, we've realized that these same elusive Majorana fermions may be realized also in condensed matter systems as quasiparticles. And I like this illustration of what I think of as a quasiparticle. You have, electrons floating around in systems, but they interact with a lot of other particles. For example, they interact with each other. They also interact with phonons and so on. And so typically you can think of the electron dressed by other particles as a quasiparticle. And this is just like a skier skiing downhill, where as the skier is skiing down, he collects this cloud of snow around him. So the skier and the snow cloud around him become one entity going down the slope. And that's what a quasiparticle is in a solid state system. So we've realized over the last 15 years that Majorana fermions can actually be realized as quasiparticle excitations in condensed matter systems. And this has been really exciting for many different reasons. One of the reasons is that Majorana fermions are actually non-abelian particles. So when you exchange two Majorana fermions, you don't get just a plus sign or a minus sign or even a phase. When you exchange two Majorana fermions, you might end up in a completely different state. So that's what a non-abelian particle is. And you can actually use these Majorana fermions in solid to understand the properties of non-abelian particles. The other reason Majorana fermions are interesting, if we can realize them, it's been shown that they can be used for fault-tolerant quantum computation. And the reason for this is that a Majorana fermion, as I would show you today, is actually made up of, so you take an electron and you split it into two Majorana fermions, and these two Majorana fermions can live quite far from each other. So it's very difficult to disturb these Majorana fermions, because in order to actually combine them back into an electron or to disturb them, you would have to disturb both at the same time. So these Majorana fermions are very good for fault-tolerant quantum computation. And so you can make gates. And so here's some example of how you can make quantum gates using these Majorana fermions. When you exchange the Majorana fermions, you can do quantum operations. So there's a very nice review on topology and Majorana fermions that was written by Jason actually in 2012. So if you're interested in how Majorana fermions are generated, I urge you to read this review. So let me just give you the gist of how you might be able to generate a Majorana fermion in a solid. So how do you construct a Majorana fermion? What do you need? Well, you essentially need a situation where creating a particle and creating an antiparticle are the same. So in a solid, what you need is some kind of particle-hole symmetry, where creating a particle and creating a hole are the same thing, or at least the operators are very similar. And the one thing you can do to get into this situation is to use a superconductor. In a superconductor, the low energy excitations are actually both these so-called Bogoliubov quasiparticles. And these Bogoliubov quasiparticles are actually superpositions of electrons and holes. And you already can see here that a Bogoliubov quasiparticle is chargeless, because as long as the electron part of it and the hole part of it are equal, the net charge of a Bogoliubov quasiparticle is 0. So that's already promising. And there's also particle-hole symmetry in this Bogoliubov quasiparticle. So a superconductor is a very good place to start looking for Majorana fermions. So let's take this superconductor. This is just a normal superconductor, and demand that the creation operator and the annihilation operator, that is the creation operator for electrons and holes, is identical, or in this case, this is not exactly electrons and holes, but a creation operator and annihilation operator is exactly identical. If you demand that, you realize that what you need two things. One is the electron and hole composition of this Bogoliubov quasiparticle needs to be the same, which can be arranged. But there is a problem. If you want to make these two equal, then you see here you have a spin up particle and here you have a spin down particle. So the spins are flipped. So if you want to realize these Bogoliubov quasiparticles as Majorana fermions, you need to somehow get rid of spin as a separate degree of freedom. So the question is, how do you do that? So what kind of superconductor can you have where you can eliminate spin as a separate degree of freedom? One way to eliminate spin is to use superconductors where the pairing is triplet. By that, I mean the following. So normal superconductors pair electrons of opposite spins as shown here. However, you can imagine having a superconductor where you pair only same spin electrons. And when you have such a superconductor where you have pair same spin electrons, you can actually get excitations in such a superconductor where the Bogoliubov quasiparticles look very much like Majorana fermions. The problem with this idea, though, is that you need this sort of a very different kind of superconductor called a triplet superconductor. And there are very, very, very few known triplet superconductors today. Okay, so the second possible way of creating Majorana fermions is to use sort of a combination of things. So let me show you what that is. A lot of people have been studying this kind of geometry for quite a long time. So here you use a semiconductor, which has very strong spin-orbit coupling. And you place that on an S-wave superconductor, and then you turn on a magnetic field. So if you can do all of these things, then it's been shown that you can realize Majorana fermions. Okay, and so you can see that the geometry here is pretty complex, and so you need a simpler system to realize Majorana fermions. And the third way to potentially, actually there are many, many ways, I'm just showing you three. A third way to realize Majorana fermions is to use these things called topological insulators. So let me just sort of digress into this world of topology, just extremely, just very briefly. So if you looking through the eyes of topology, the shapes above are topologically identical to each other and topologically distinct from the state below, from the shape below. In fact, topology is the mathematics of shapes, and you can actually characterize shapes by using something called the Euler characteristic. And what this characteristic really captures is the curvature of the geometric object. For example, topologically speaking, this sphere is different from this donut and is different from this double donut. And what the most important thing is, if you took a sphere like this and you deformed it adiabatically without making any hole, the topological property, which is its Euler characteristic pi, remains a constant. So you can classify mathematical shapes, geometric shapes, by using this Euler characteristic. And a sphere has a characteristic of 2, a donut of 0, and a double donut of -2. And in order to go from a sphere to a donut, you have to do something quite drastic, like taking out a chunk of the material. So very similarly, you can define topological invariance. The Euler characteristic is one such example of a topological invariant. You can define topological invariance for solids by looking at the band structure in momentum space. So I don't have to go into the details of what in the band structure defines the topology. One shortcut way of thinking about it is actually, if you look at the parity of the wave functions at high symmetries, then just by looking at that parity, you can say what topological class the solid falls into. However, for our purposes, all we need to know is that band structures can have different topological properties. So you can have a normal insulator and you can have a topologically non-trivial band insulator. And it turns out that if you were able to make such a non-trivial topological insulator, then wherever it meets another material with a different topology, you're expected to have special states at those boundaries. So for example, right, all around this material, there's vacuum. So all around, on all of the surfaces of this material, you're expected to have these two-dimensional surface states. And these two-dimensional surface states are bound to exist as long as this topology of this material doesn't change. So these two-dimensional surface states are really interesting. They have unique properties that I'd like to illustrate here. So here on the top is the dispersion, the energy momentum relation of a two-dimensional surface state. And if you contrast that with a conventional, what a conventional electron looks like, so if you have conventional electron surface states, then the energy momentum dispersion would look like this. It would be parabolic because the electrons have mass. And at each energy, you have a spin up electron and a spin down electron. Whereas these special surface states, the first thing is the electrons behave like massless Dirac fermions. They behave like relativistic particles. Moreover, at any given energy and momentum, you have only one electron, not two. The most important thing here is that once you know the momentum, the spin of the electron is completely defined. This means that you only need one quantum number, not two quantum numbers, to define the electron. So if you can actually completely throw away the spin and only talk about the momentum of the electrons. So because of this so-called spin momentum locking, you can use these topological insulators to create Majorana fermions. Okay, so in fact, that's what Charlie Kane and Liang Fu proposed. They suggested that you can use topological insulators to create Majorana fermions. And they suggested these two different geometries. One is you take a topological insulator and you put it to superconductor on top, and then you turn on a magnetic field. And they said that when you do that, in the vortex cores of the vortices, you should trap Majorana particles, which you should be able to measure. The other idea is that you take the same topological insulator, put a superconductor on top, and somehow engineer a situation where you have a pi phase shift in the superconducting autoparameter. And if you do that, then at the boundary of such a system, you get propagating Majorana fermions. So these Majorana fermions are not bound to the vortices. They can actually move in this direction. So that was the suggestion. And I just wanted to flash the slide because I mentioned right at the beginning that if you can create these Majorana fermions, you can use them for topological quantum computation. There's a very nice review here which talks about how you can braid the Majorana fermions for quantum computation. Okay, so this is the kind of thing that I'd like to talk about today. And I'd like to show you evidence for Majorana fermions in this material, iron selenium tellurium. Okay, and before I do that, maybe I should pause and ask, are there any questions about what I've said so far? Okay. So what we're trying to do is realize Majorana fermions in a solid state material. And like I said, one way to do is to find a topological insulator, which can be proximatized with a superconductor. As it turns out, this material does both. So iron selenium tellurium is a superconductor. It's been known for a long time as an S-wave superconductor. And very recently, actually in 2015 and 18, it was suggested that this material may also be topologically non-trivial and may have these exotic linearly dispersing surface states on the surfaces. So then what you have is a situation where you have both things in one material. You don't have to add a superconductor to a topological insulator. Instead, you already have a superconductor and a topological insulator built into this one thing. So now the question is, you take this material and turn on a magnetic field, can you find Majorana fermions inside the vortex course? That's the first question. And the second question is, can you find areas in this material where you have pi phase shift between two regions such that you can realize propagating Majorana fermions? So those are the two questions I'd like to answer. So this is the phase diagram of this material, and the actual composition we are interested in is right in the middle, which is 50% selenium and 50% tellurium. This is just for the experts. I just wanted to show the band structure. There are many different pockets, electron and hole pockets inside the Brillouin zone. And actually, each of these things becomes superconducting with a different gap magnitude. And so you'll see that when I show you the STM spectra. So in 2018, ARPAS studies first showed that in here, in this little gap, you can see Dirac surface states. So this is what created a huge amount of excitement in the community. And this is what you need to realize Majorana fermions. Okay, so now I'm going to talk about the probe that we use in my lab, which is scanning tunneling microscopy. And some of you may not be familiar with this, so I want to just give a very, very brief introduction. An STM is actually a very simple tool. And the way it works is you bring a very sharp needle into sort of close proximity with a surface that you'd like to study. So within a few angstroms of the surface. And then you apply a small potential difference, and electrons can tunnel across the vacuum barrier from the tip, we call this the tip, from the tip to the sample or from the sample to the tip. And the measurement that we make in STM, there's only one measurement that we make, and that is the magnitude of the tunnel current. So we measure the tunnel current as the tip is swept across the sample to obtain topography. We can measure the tunnel current as a function of bias voltage to measure density of states and so on. So it's a very simple technique. The only problem is because the tip is so close to the sample, just a few angstroms, it means that any noise or vibrations can actually disturb the system quite a lot. So our experiments are always in the basement inside a soundproof room. And not only that, they're mounted on these vibration isolation legs and so on. So the experiments I'm going to describe today were done at very low temperatures, 300 millikelvin, not that low for the dilution fridge people, but still low temperatures. And one of the reasons is that superconductivity happens at low temperatures, but also at low temperatures, you can get very high energy resolution. Okay, so a very nice pictorial way of thinking about the STM is the following. You can imagine the sample and the tip as basically filled buckets of electrons up to the Fermi sea. When you apply a potential difference, so when they're both brought into proximity with one another, the two Fermi energies line up, and so there's no tunnel current. When you apply a small potential difference between them, you can lift the Fermi energy of one with respect to the other, and now electrons can tunnel from the filled states of the sample to the empty states of the tip. And you can see actually that the number of tunneling electrons should be proportional to the integrated density of states of both the sample and the tip. So with STM, we can measure density of states as a function of position. And density of states is number of states per unit energy. And it's a very, very important indicator of all the physical properties of your material. For example, if you have a superconductor, we know that all the electrons are paired into Cooper pairs. So at low temperature, if you measure the number of states near the Fermi energy, you'll get 0. So at low temperatures, below the transition temperature, there are no states below the Fermi energy, and above, near the Fermi energy, and only above a certain value of energy, do you start seeing states. So when we measure dI/dV in a superconductor, we get a sharp peak called the coherence peak at the gap edge, and then 0 density of states. So in my lab, we have a few different scanning tunneling microscopes. The STM that we used for this work that I'm going to show you is this one. And this has 11 Tesla magnetic field and can go to 300 millikelvin temperatures. Okay, yes? Yes, with a superconductor. So this is the crystal structure of iron, selenium, tellurium. The reason I show you this is that when we prepare surfaces for STM studies, we actually break the surfaces. So we cleave the material. So this particular material is really nice. It cleaves right here, and it exposes the tellurium plate. So you can see these yellow balls. Those are the tellurium atoms. And this is the top view. This view shows all the 3 layers of the FeSCTE plane. So you can see the top tellurium atoms, the middle iron atoms here in blue, and the tellurium atoms below. The important thing to notice here is that the tellurium atoms on top and the tellurium atoms underneath are actually shifted from each other by half a unit cell. And that means that when you look at this crystal, you realize that this what you call the top tellurium atoms, you could actually take this layer and flip it over, and then these things would be on the top, but they would be shifted by half a unit cell. So you can imagine that the crystal chooses this configuration, but the same crystal might have other regions where this thing is flipped. So you can have a lot of boundaries in this material between one configuration and another. Okay, so you can just take this thing and flip it, and this thing will be at this position, which is half a unit cell shifted. So when we look at the surface with an STM, we only see these top tellurium atoms, which form this top plaquette. And so this is what an STM image looks like. And first, if you look carefully, you might be able to see the dots that are the atoms, but we can zoom in. And now you see the dots clearly. Some of them are selenium and some of them are tellurium. So you can see all the inhomogeneity here. That comes from the fact that you have 2 chemical species. But you see the nice square lattice formed by these atoms. And now at low temperatures, you can ask whether this material is superconducting. And so you can so here at this point, you can take a spectrum. And as I promised, the spectrum looks exactly like you thought it would. You see this sharp coherence peak at the gap edge, and then basically the density of states drops to 0. So this is literally 0 density of states inside the gap. One interesting thing is that you don't have just one coherence peak, you have many. In fact, sometimes you have even 3 coherence peaks at the same point. That is because those different pockets that I showed you have different gap magnitudes. And then you can compare our, we have a huge amount of statistics. We can go to every point on the sample and measure the gap. And so if you compare statistically our gap magnitudes with what was seen by angle resolved photo emission, basically our numbers match really well. So from all this, all I want to tell you is that it does look from our data that there is indeed a new gap associated with this special surface state. Okay, so now let's turn on a magnetic field and ask, what do we expect to see? When you turn on a magnetic field, what you expect to see are vortices, and inside each vortex, you should see, if this is topological, if this is what we think it is, you should see a sharp peak in the density of states right at the Fermi energy, and that sharp peak is your Majorana bound state. Okay, so now let's look at what we see. So first, what I'm going to show you is a spatial image of the density of states at zero bias. Now, if you don't have a magnetic field, this density of states at zero bias is zero, so it should look blank. So now let's see what happens when you turn on a magnetic field. That's what it looks like. So these are regions where it's dark, so there's nothing going on, it's just a superconductor. But then you have this periodic array of bright patches, and each of these bright patches is a vortex. Okay, so this is what happens when you turn on a magnetic field. Now let's look at one of these bright patches and look at the density of states inside this bright patch. And here's a line cut. So far away, right here, you see the superconducting gap. At the center, you see the sharp peak exactly at zero bias. And this is what you expect for a Majorana fermion. So this zero bias measurement of the sharp peak in the density of states was actually first done by Hongding and his collaborators in China in 2018. What they found is that they find these nice zero bias peaks, right? You see it here. But only 30% of the vortices showed these zero bias peaks. So there were a lot of questions about how do you know this peak is a Majorana fermion? Why do 30% of the vortices show it? What about the other vortices and so on? So the question you have to ask, right? So it's very nice and tempting to associate a zero bias peak with a Majorana fermion. The question you have to ask is, okay, you have a zero bias peak, but what's the real proof that it's actually a Majorana fermion? So let me try to address that first. So when you have a superconductor and you turn on a magnetic field, you get this vortex. That is that the flux has penetrated your superconductor, and now the superconductor tries to screen the flux. So there's a supercurrent that's going around the flux lines, and inside this area where the supercurrents are going round and round like crazy, inside there you have a normal region. Okay. So inside this normal region, you can have low energy excitations, which are your Bogoliubov quasiparticles. And in fact, that's why you get these Majorana fermions at all. But remember, what you have is a little area inside a superconductor, right? Where these Bogoliubov quasiparticles are confined. So because of this confinement, you can have quantum well states made up of Bogoliubov quasiparticles. And these are called Cayley-Dejean states. So in any type 2 superconductor, if you turn on a magnetic field and you look inside the vortex core, you'll get these Cayley-Dejean states that are actually peaks in the density of states. So these are not Majorana fermions, these are just trivial bound states inside the vortex core. So the question is, how do you distinguish these trivial bound states from Majorana bound states? And the first thing is that these trivial bound states are not supposed to occur at zero energy. In fact, the energy of these Cayley-Dejean states goes as delta squared over E, where delta squared is the gap energy, and EF is the Fermi energy. So you can calculate this value for this material, iron, selenium, tellurium, and what you find is that the energy of the Cayley-Dejean states should be about 100 microvolts. So the first Cayley-Dejean state should be 100 microvolts from the Fermi energy. So we have another STM person in Japan called Hanaguri, and he did some very nice work, very low temperature STM, 50 millikelvin STM. And he showed that the peak that's at zero bias is at zero to within 20 or 30 microvolts, and very far from where you expect the Cayley-Dejean state to be. So 100 would be right here. So the zero bias peak that I'm calling Majorana fermion is actually exactly at zero to within the resolution of the system. The second interesting thing that was found with these Majorana, with these zero bias peaks is the following. The Cayley-Dejean states, actually, you can have many of them. You can have many of them, their energy spacing, right? Their energy spacing goes as half integer times delta squared over EF. So that's a very definite prediction. Whereas what you can show is that even for Majorana fermions, you can have many such bound states, but those energy spacings go as integer times delta squared over EF. So what Hong Ding and his collaborators, Hong Jung Guo, showed is that for the Majorana modes, you do find the so-called integer spacing. So the combination of the fact that you have a zero bias peak, which is pretty much at zero within instrument resolution, and the fact that you have integer spacing rather than half integer spacing, these two things strongly suggest that these things might actually be Majorana fermions. Okay. So the next thing to ask is, can you in this very magical system also see evidence for propagating Majorana fermions? Okay. And so how do you get these propagating Majorana fermions? You can get them. Sure. So they propagate along this, and eventually they have to merge into the bulk or terminate somewhere, or maybe go around the sample. Yeah. This geometry that I've shown is just a cartoon, but you might imagine if in a real crystal, they might terminate at the boundary or go around. So they follow this, and eventually they have to do something. You can have chiral, so if you had chiral propagating Majorana fermions, you can have a net current actually. But in this system, time reversal symmetry is not broken, it's preserved. So the Majorana fermions that I'm talking about are helical Majorana modes. There are two copies of them. So one's propagating this way and one's propagating this way. So they could go into the bulk eventually. They could mix and go into the bulk. So what do you need? You need superconductivity. You need something that's topologically non-trivial. We have both of these in this one system. And finally, you need these regions where there's a pi phase shift in the superconducting order parameter. And the question is, how do you get this? And so interestingly, actually, this material gives you this as well. So there was a calculation in 2013 for these kinds of superconductors that I've been talking about today that showed that because of the nature of the material, the way you look at the hoppings in this material, you can show that the superconducting order parameter actually has a phase shift layer by layer. So this is the top tellurium layer. This has a negative phase, the bottom has a positive phase, and so on. So there's a layer by layer phase shift in the phase of the superconducting order parameter. So like I told you, this material, you can actually have regions where the crystal is flipped. So imagine you have a region where on one side, you have this kind of stacking, and the other side, you have a different stacking, basically a flip stacking. It's called a stacking fault. Then right at this boundary, you have the situation where perhaps superconductivity shows a phase shift. So we went searching for such domain walls. So a lot of our sample looks like this, very nice, no domain walls. But then once in a while, you can find regions where domain walls snake across the sample. In order to figure out if it's the right kind of domain wall, you have to zoom in, right? This is a zoomed in view. And you see atoms on this side, atoms on this side. You take a Fourier transform. What you notice is that one of the Fourier peaks, this one and this one, it's split into two. And that's a sign that you have a phase shift in the atoms between this side and this side. So you already know that there's a phase shift. So the question is there a pi phase shift? Sorry, what I mean by that is, are the atoms shifted by half a unit cell? And we can see that from topography. We can also see it by doing some Fourier analysis that I don't want to get into right now. Okay, so now let's ask, what do we see at the domain wall? Okay, so this is what we see. So far away from the domain wall, this is the blue dot. You see the superconducting gap. This is zero density of states. At the domain wall, you see finite density of states inside the superconducting gap. But more remarkably, this is really interesting, it's flat, meaning that the density of states has no features. There are no peaks, nothing. The density of states is flat. So when I first saw this, I was very struck because I've studied a lot of superconductors, over the last couple of decades. And usually when we go to a defect and we look at the density of states, either the gap gets smaller or there are sharp peaks inside the superconducting gap. I'd never seen something like this where the density of states is actually uniform inside the gap. So this is just to show that it's true across the domain wall. So as you go across the domain wall, you can see that the density of states, this is a color plot of the density of states. It's basically featureless. So this flat density of states it actually disappears above the superconducting transition. So above TC, you get this orange spectrum. So this is a property of the superconductor. And the actual spectrum away from the domain wall and all the domain wall are not that different. So this is not a simple density of states effect. So the question is, what is this? So you can ask the following question. Like I told you, if you have a pi phase shift between the two superconducting regions, then what are you supposed to get at the domain wall? That's what Liang Fu and Charlie Kim showed us. What you're supposed to get is these helical Majorana fermions. And these things have linear dispersion and they propagate in 1D. So you can ask a question, what is the density of states of a linearly dispersing mode? And the density of states of such a mode is in fact featureless, it's flat. Okay. So if you have linearly dispersing modes along here, what you expect to see is a flat density of states. And that's exactly what we see. So we can do more. What we can do is we can actually ask, how are these things localized near this region? And what theory tells you is that as you get, if you look at the states right at zero, they should be pretty well localized. But as you get away from zero, the states should get broader and broader in real space until they merge into the bulk. So here are maps as a function of energy. This is the domain wall. And so at zero energy, you can see a nice localized mode. And as you increase your energy, this mode, the spatial extent of the mode grows. And so eventually, around close to the gap edge, this mode has in fact merged with the bulk. Okay, so that's what we see. And so in this material, I hope I've been able to show you that we see two kinds of features. One is these vortex core states, for which there's mounting evidence that they behave like Majorana fermions. And the other is that if you have the right kind of domain wall, like a stacking fault of the right kind, then at the domain wall, we see these evidence for these propagating states. So of course, this is not the end of the story. This is, what do you want to do with these? Well, we'd like to actually move them, at least the ones in the vortex core, if you could move them around each other, then if you could braid it or see evidence for non-abelian statistics, that would be quite amazing. I think that's it. I'd like to finish by thanking my collaborators. The work was done by my former postdoc, Zhenyu Wang, with the help of my graduate student, George Rodriguez. We had a huge amount of theory support from Taylor Hughes at University of Illinois Urbana-Champaign, as well as Dirk Moore from UIC. And we got really nice high quality single crystals, which all this work was on single crystals grown by Genda Gu in Brookhaven National Lab. Thanks a lot.
Okay, so questions from the audience?
I will ask one question.
Sure.
This vortex core stage for S-wave superconductivity, that's well known, but these materials are sign changing S-wave.
Correct.
And so have people done theoretical calculations to demonstrate that it's still also one half?
Yeah, that's correct. So I think that when they wrote this paper, let me actually get to the. That's correct. That's correct. So the paper on this paper has. So this paper has, I think it's the science paper, has calculations by Liang Fu as well. And Liang Fu's calculations show that for this material, I don't think there's any difference. I mean, I don't think there's any difference between the Carrel-Legendre states for an S plus minus superconductor and an S-wave superconductor. Because S plus minus is just the relative phase of superconductivity between different pockets. So if you just look at one pocket, right, it's just an S-wave superconductor.
Yeah, but if you just look at one pocket, that's in momentum space.
Correct.
So in the reciprocal space, that can be, I'm sorry, that's in, that's
Yeah.
in reciprocal space.
Yeah.
So in real space, I'm worrying about possible superposition of both electron and hole contributions, and therefore maybe the original one half integer might actually become integer. I do not know. I was just wondering.
I don't know the answer to that, but you know, I think that since Liang was involved, he might have thought about it. But if I see him next, I'll ask him.
Well, we should look at the theoretic, see if people have done the rigorous theoretical
For S
calculation
plus minus
of
superconductors.
sign changing S-wave. Here's
But
different from just
there
one
is one thing I do want to say though. This material has a mixture of normal vortices where you have half integer spacing and these Majorana bound state vortices where you have integer spacing. You see both in the same system. So it cannot be just an S-wave superconductor. Then you might ask, why don't all vortices show Majorana fermions? And they attribute that, and we have all seen this, there's a huge amount of spatial inhomogeneity in the gap magnitude. And also the position of the Fermi energy with respect to that Dirac surface state, that moves a lot. So you can imagine that within the same material, you have regions where it doesn't quite look topological and other regions where it's actually topological. So that might explain why you have different kinds of vortices, but they do have both. So it's something to think about.
Right. That's certainly a valid point that's
interesting.
Yeah. If I may ask another question, hopefully this will be quick. And so when you mentioned along these boundaries, these supposedly the unknowns will be propagated.
Yes.
How do I physically picture it? I don't see one. This is in the absence of in the presence of emitted fields or in the absence.
Okay. So if you break time reversal symmetry, then you get chiral Majorana fermions, which propagate only in one direction.
Right.
But in the presence of time reversal symmetry, you can get helical without any magnetic field. You can get helical Majorana. These are just boundary modes.
Right.
And so you can get helical Majorana fermions. There's no problem.
Yeah, so I was just trying to understand what you mean by propagating, because
so by
we're just seeing some static spectrum, right?
Yeah. You're absolutely right. So if you have, so the difference is between having something, I'm just going to draw a chiral thing just for simplicity, and a bound state. So this bound state is basically bound to the location, like if you have a potential well, you have a bound state inside the potential well, and it's basically confined to the potential well, it can't go anywhere. Whereas these propagating states this is in 1D, they can actually move along this boundary, literally propagate along the boundary, just like, so what I'm trying to say is they have finite moment, like they have the possibility of moving, because this is like a band of states.
I can understand from this picture. I'm just saying, when I look at real data, how do I know that I can argue that there's a propagating law?
Okay,
Just from
you cannot. The one thing I can, there are a few, again, this is all evidence that piles together to give you that information. You can't just from looking at it. The one thing I can say is, if this is your domain ball, then the mode that we see, it lives everywhere along the domain. So we don't see any gaps, or they're not like, it's not as though it's here and here and here. It lives everywhere along the domain wall. The second thing is that I don't have any other argument except the density of states argument, which is, you ask a very simple question. If you have a one-dimensional mode, what should its density of states look like? And it should basically be uniform, which I've really never seen in a superconductor before, in response to an impurity.
But it could be static or something. So the question
Oh, so that you're talking about a bound state then.
Right.
So a bound state would look like this in terms of density of states. And we do see that also for other defects, we see bound states. For example, you can have a point defect, and sometimes point defects can give you bound states in their vicinity. And so whenever you see a bound state, it looks like a peak in the density of states. Yeah, but we have no further evidence.
This can be very interesting, and it's actually a propagating mode. There should be other time-dependent signatures.
There is one more thing, something interesting. What we find is that if you measure your spectrum here, and then you go slightly to the side and measure the spectrum, when you go to the side, you can see that the density of states is actually like this. So so you can see that there are states that live here, right? So if you look at the spatial dependence of the spectrum, it provides another clue to the fact that they're actually propagating states. But yeah, there's no smoking gun evidence. I agree.
Thank you.
Yeah. Yes.
I don't really have to say very much to argue that it's Majorana.
Okay.
The flyweight spectral number, that's Majorana.
Yes, yes.
Is there anything like that in the condensed matter case?
It's very murky, isn't it? So yeah. The reason it's so murky, one of the reasons at least, is that zero bias peaks are notoriously common in condensed matter physics. There are many ways of getting a peak in the density of states at zero bias. So that cannot be smoking gun evidence.
There's no symmetry that really doesn't apply to the case for the Majorana that is considered to be.
The question is, how would you measure it? That's the problem we have. One thing is that the conductance of one of these channels is quantized. That's a pretty important thing. It doesn't really tell you that these are Majorana fermions, but it's also additional evidence. So people have been trying to measure the conductance of something like this and show that it's quantized to E squared or 2E squared, E squared over H. So you want quantization of this. I guess the only smoking gun evidence I can think of is if you can prove non-abelian statistics. That is, if you can rotate one Majorana fermion around the other and show that you entered a new state, that would be pretty smoking gun evidence. So instead of getting a plus or a minus, yeah, there's nothing I can think of. Does anyone else have any ideas?
In an ideal world, you can do a topological to
But-
prove the statistics, but it's very hard to do.
Yeah, it is, yeah.
Yeah, let's see. The link.
Just, I want to make sure that I understood correctly. You showed some slides where this topological
It is about superconductor. Yes, that's correct. That's absolutely true. And so this is an added complication. So you have bulk states, which are superconducting, which have their own vortex core states. And then you have the surface state, which is this Dirac, this topological surface state, which also becomes superconducting. So it has its own gap. And those electrons, those surface state electrons, they also respond to the magnetic flux by circling and spinning. And it's inside. So you do have both things. You're absolutely right. And so the only thing I can say there is we do know for the system that the bulk Cayley-Dejean states, these vortex core states, are not supposed to be at 0. Instead, they're supposed to be at 100 microvolts. Whereas the states that we see at 0 are very close to 0 within about 30 microvolts. So by that I mean they're really at 0, but 30 microvolts is the resolution of the 50 million Kelvin system.
But then this bulk state actually depends on the magnetic, so it's not should extend the high end.
So the bulk state, so the vortex states do penetrate in this direction. That's correct. So the bulk states do go into the bulk, the vortex core states. You're absolutely right. What are you saying, sir?
It's not a discrete spectrum like
You can have a range of, so you can have a band. You can have a band. Yeah. So actually, I think someone was asking me this today, and I told myself I would take a look. Okay, let me look at this carefully. So the data here is the red curve. This is not my work, by the way. This is Hanaguri's work because he has the lowest temperature STM. So you need the low temperature because these differences in energy are very, very small. So here you have the data in red. It's possible that there's a lot of density of states here underneath all this. And that could be coming from all of the vortex core states that you're talking about. Yeah.
Last question from Nathan.
So looking forward to these more smoking gun types of experiments. We're talking about moving the vortex cores around, manipulating these. Kind of curious experimentally, what goes in, like what requirements would you need to have in order to do this? Or would you be looking at finding like a domain island and using that as a sort of naturally given interferometer or something?
The real problem, I think, is first to actually do the experiment, but then to ask, what can you measure? We can't measure phase. What can we measure that will tell us, for example, that we have non-abelian statistics? So that is very, very tricky. I don't think I have a good answer for that question. I'm sorry. I think that I cannot do that unless I could So I can imagine a thought experiment, for example, where I have a magnetic tip and I take the magnetic tip and I drag the vortex, one vortex around the other vortex. If I could do that, then my question would be, what is my measurement that shows that I have entered a new state? And I don't know the answer to that. So similarly, you can imagine transport experiments where you have Majorana bound states that can be moved by electric currents, and you can achieve this kind of braiding. But the question is, what is the measurement that proves that you've actually achieved braiding? So this, I don't have the answer to this right now. Yeah. I don't think it's that easy. Yeah.
Maybe remaining questions can come down and be asked in person. Since we're over time, let's thank Vidya again.